Well, now we start the last subject covered in Module 2, which is matrices in our engineering math course. And that is applying our matrix methods to dealing with systems of differential equations. We'll be limiting the set. For one thing, there'll be linear differential equations. But let's just see how this goes. Let's say, first of all, you just had two variables, x and y, and the derivative of x involved both x and y. The derivative of y involved both x and y. So we solved these earlier in engineering math individually. It didn't involve both equations. We used Laplace transforms to solve. Probably other ways to do it. And if we use Laplace transforms, we could have done it with multiple variables like this, but it would involve more algebra, things like two equations and two unknowns type stuff. But anyway, we're going to use matrix methods. So you could take these two equations and put them in matrix form. Put our derivative stuff on the left, and then here's the non-derivative stuff on the right. See, here's dx dt equals x minus 2y, right? Okay. Same with the equation on the right. All we did was put it in matrix form. Say, well, that worked because it was only first order equations. Nothing over dx dt, second derivatives. Let's say you had this. It's all one variable, but there's a second derivative. Well, you can define another set of variables that are defined as these original variables and their derivatives. Let's say x1 equals y and x2 equals y prime, meaning the derivative with respect to e here. Then what's the derivative of x1? It's y, so its derivative is y prime, which is x2. What's the derivative of x sub 2? Well, it's y prime, so its derivative would be y double prime. We can express that in terms of the rest of it by this equation. So we can express it all in terms of other x's. Anyway, it ends up, you could put it in this matrix format. Derivatives on the left, the rest of it on the right. This one had an input, external input f. These two didn't, it's just x and y. So here's the idea. Here's the general form. Well, that falls into the general form I'm going to call state space. Vector x, or the column matrix x, your variables. Its derivatives on the left, and then ax plus. So in general, these would be the scalar versions of your equations. This is the matrix version. Again, it's still state space format. And in general, these coefficients could be functions of time varying, and you could have these external inputs. A could be time varying. This matrix A could be time varying, and we could have an F. But in our short little course, we're not going to do that. For us, A is going to be all constants, not functions of time, and the F is going to be 0. So for our little course, and we have as many equations as we have unknowns or variables. So A is square. All the little a's are constants, meaning A itself is a constant matrix. And F is 0, meaning the equation is homogeneous. We have a few theorems about such systems. For one, if we're given a bunch of particular solutions, a linear combination of them is also a fundamental set. There exist n linearly independent solutions to the homogeneous system of equations and variables. So we're going to get n linearly independent solutions to this guy. And the general solution is then the linear combination of those n particular solutions. So we go about finding the x. The x is the matrix of unknowns, the vector of unknowns, or the variables. Let's assume it has this form, where k is some vector, n by 1, e to the lambda t. Then this x's derivative with respect to t would be lambda times the original x. So here is x prime equals ax. That's the equation we're solving, right? This is the equation we're solving. X prime equals ax. And if x equals this, x prime equals ax becomes this. Divide out e to the lambda t, it is a non-zero scalar. I'm left with this equation, which is, the eigenvalue problem. We can find the solutions by solving the eigenvalue problem. That gives us the lambdas and the k's. There you go. All the hard work is stuff we already did in previous videos. So one thing, if all the eigenvalues are distinct, then it's going to give us n distinct eigenvalues, and eigenvectors, these k's. And the solution will then be this linear combination. All these arbitrary constants, the c's, and then eigenvectors and eigenvalues. So we can construct, once we solve the eigenvalue problem, we can construct a solution for a system. Let's take a system. Here's like those two scalar equations. So we'll put it into state space form. I have a -4, 2, -5 adds 2 in my little A matrix. That's A. Now I go about solving the eigenvalue problem. First, find the eigenvalues. Subtract lambda off the main diagonals and calculate that determinant. I get this. I get a quadratic. I can factor it. I get my two eigenvalues, right? And when it's 2 by 2, remember the trick? First, for lambda 1, which was 1, we're going to subtract 1 along the main diagonals. So it'll be -5, 1, and then the 2 and -5. And remember the trick? The eigenvector will be this guy on top of the negative of this guy. So it'll be 2 over 5. Good little trick you can use when doing 2 by 2s. I covered it in a previous recording. And in this one, see, I'm going to add 3 to the main diagonal, so I'll have -1, 5. Here we go. It'll be 2 over 1. There's my 2 eigenvectors. Here's my solution. This eigenvector went with that eigenvalue. So it's e to the 1t. And this eigenvector goes with e to the -3t. Those two arbitrary constants. By the way, those arbitrary constants you would solve them if you had some kind of boundary condition. We're not going to do those problems. We're not going to do initial value or boundary value problems. We're just going to do the general solution. And this is the general solution and how you write it. Let's see. If you don't have distinct eigenvalues, but you have n linearly independent eigenvectors, it's the same solution. It'll just be that some of these eigenvalues are repeated. I do not cover the case where you don't get where you don't get n linearly independent eigenvectors or an n by n matrix. Remember, that was one of those little tricks or things that could crop up. Anyway, it's just a little bit more complicated and not worth the time for this course. I'm just showing you some applications of why we're doing the eigenvalue problem in the first place. Systems of differential equations. I think I'll do this example and then stop the record. Then we have these three differential equations in three variables, x, y, and z. So hopefully you can go from this to what a is in the space formula. 3 minus 1 minus 1, 1, 1 minus 1, 1 minus 1, 1. Subtract my lambdas off the main diagonal, the rest of it stays the same. I get one hellacious polynomial. And in fact, I cheated here. You'd have to factor a cubic, which is too much to do. So I'm just going to give you that answer. Here's the eigenvalues. We have a repeated eigenvalue. I'm not going to go through at least this first one. Well, let's do it. The unique one is 1, so I'll subtract, lambda will be 1. So 3 minus 1 is 2, 1 minus 1 is 0, 0. Here's the, call that matrix now. This is the A part. Start doing, not sure why I ended here. Start doing Gaussian elimination. This will tell me that K1 equals K3. And this one tells me K2 equals K3. So they're all equal. So that eigenvector is all 1. Now for the repeated eigenvalue. It's 2, so I'll have a 1 here, minus 1 here, and a minus 1 here. Pretty easy Gaussian elimination. Oh, I have 2 rows of all zeros. That means 2 free parameters. I'm going to get 2 linearly independent eigenvectors out of it. If I only had 1 row of all zeros, I'd only get 1 linearly independent eigenvector out of it. And I don't cover how to do the solution to the differential equation in that case. But in this case, we're going to get 3 eigenvectors, linearly independent eigenvectors for this 3 by 3 matrix. We do this 1, 0, 0, 1 trick yet again. One of the subtleties in all this. I could write this like this. Well, this says K1 minus K2 minus K3 equals 0. I could write it as K1 equals K2 plus K3. I have 2 free variables. I do the 1, 0, 0, 1 trick. And I'll say the first time around, I'll set K2 to 1, K3 to 0. The second eigenvector, I'll set K2 to 0 and K3 to 1. When K2 is 1, and K3 is 0, I get a 1, 1, 0. When K2 is 0, but K3 is 1, I get a 1, 0, 1. Here's my 2 linearly independent eigenvectors for the eigenvalue. So here's the solution. Let my little coefficients, don't forget them, the eigenvectors, and they have to go along with their eigenvalues. So this guy goes along with e to the t, and these 2 guys will go along with e to the 2t. Okay, we'll get to some other aspects of this, including complex eigenvalues, but I'll do that in another